Drones or unmanned aircraft systems are particularly suitable for performing tasks that are tedious, risky for people on board, or in environments inaccessible or harmful to humans. Drones are already used in some high-value applications like organ deliveries or search and rescue. They will bring even more important benefits to mankind. Drone operations present risks to people and goods on ground, as well as to the other aircraft in the same airspace. Civil and commercial use of drones requires to exhibit at least an equivalent level of safety to current manned aviation, especially for riskier missions like those where the unmanned aircraft is required to go beyond visual line of sight, BVLOS, or to fly higher than 400 feet, or to be operated in complex environments such as urban or airport areas. A drone operation has 3 steps: the preparation phase occurring before the flight, the execution phase during which the flight is performed, and the post-flight phase, which includes data processing if necessary. The flight preparation is the most time-consuming and important compared to the 2 other phases, as it is the phase during which risks are assessed and mitigated, and all authorizations from regulators and authorities must be granted. Unfortunately, most of the contribution in literature supported the flight phase, and few considered the preparation phase. Previous work also focused on missions which did not involve to request waivers or operating authorizations. This creates a lack of field data to inform the design of future systems. Our goal was to better understand the process used by professional drone operators when they prepare a drone mission that necessitates authorization. Our contributions are threefold. First, drone professional practices during mission preparation. Second, a model of a collaborative process of operating authorization requests, along with 9 recommendations to support the design of safe drone mission preparation tools. Third, identification of design concerns and opportunities to inform future research efforts. For that, we conducted interviews with 14 drone operation managers working for operators of various sizes. Each operator had already performed at least 1 mission requiring an operating authorization with a detailed risk assessment, either using safety methods recognized in Europe and the world, or having conducted cross-border/international operations. 2 complementary interviews with 2 teams from the French civil aviation safety, so-called regulators in our context, those who assess the request and might or might not grant the operating authorization. We used thematic coding techniques derived from grounded theory for the analysis. It resulted in a descriptive model and the identification of an initial set of recommendations. Finally, we consolidated our result using a follow-up questionnaire. We found that to carry out a complex mission from a safety point of view, a considerable preparatory phase was necessary before the actual flight, which is consistent with the literature and even more pronounced compared to professional missions not requiring authorization. This stage involves highly technical tasks, the involvement of several stakeholders, and the production of numerous documents. For an extreme case, one participant commented that it once took 6 months of work for 20 minutes of flight. The mission preparation phase can be divided into 3 main steps. First, establishing a concept of operation. Second, managing risks. And third, obtaining an authorization. The concept of operation is used to clearly outline the operation that will be performed as part of a mission. It is a description of what is going to be done with a drone, where and when, with which system, and with which participants. Each CONOPS poses different problems and leads to different solutions. Operational risk assessment serves to identify and mitigate the risks to guarantee a targeted level of safety. It is an analysis that defines the requirements that an operator will have to meet before flying a drone. The European regulation recommends the use of a specific operation risk assessment (SORA) methodology to conduct this analysis. Last step is to obtain an authorization. Operators must submit a file to the regulator containing the concept of operation and the risk assessments, as well as other administrative approvals according to each case. During the examination, successive revision can be made according to the regulator's request for clarification or more effective mitigation means. From a regulatory prescription, the process to get an operating authorization can be represented like this. An operator applies with a file including an operational risk assessment. In return, the regulator will grant the authorization. But we found that it's a bit more complex, with the 3 steps explained previously. And here is a simplified model of the real processes described by the operators and the regulators. We can see several other actors involved and several tasks. Some of them even include loops, which can cause even more complications and delays. Expert users have developed strategies to make their processes more usable, that is, maximizing safety while taking into account the other dimensions: business goals, speed, collaboration, regulatory framework. We provide 9 recommendations to support these processes and their priority for complex missions. They are detailed in the article, but here we only evoke 3 of them. RC2. Systematically identify and use operational parameters to describe a mission. Several operational parameters can be found on a continuum according to the degree of which they can be configured or acted upon by the operators. From the interviews, the most recurring operational parameters were the distance to the safety pilot, which determines the nature of the flight, VLOS, BVLOS, the trajectories and the height of the aircraft, and speech, which are used to calculate the safety margins, of the flight's time and place, which are used to know the characteristic of the environment, like whether it's populated or not. RC4 support exploration of operational parameters and estimate their impact on mission safety. The search for solution to control the risks is a creative process. Mitigation depends on the operator's choice, and some small details can change everything in the result. This recommendation requires that operational parameters have been identified and used as suggested by RC2. The head of regulator confirmed and commented that it would help operators to explore options that could simplify their procedures while improving the safety of their operations. RC6 support representation and manipulation of operational parameters on maps. The use of maps is essential during the operational risk assessment. The map serves as a communication tool, but also as a visual thinking tool, exposing some potential safety issues like populated areas in the vicinity or safety buffers overshooting the operation perimeter, as illustrated in the figure. From our results, we unveiled both design concerns and design opportunities. Let's discuss about concerns. First, there is a tension between safety and business goals. The client thinks big, but the operators and the regulators will make sure that technical and regulatory feasibility are possible before proceeding further. Second, there is another tension between safety and automation. Supporting thinking about possible consequences on the operation's safety is preferable to going faster, which can be the case if one's filling in forms quickly to get rid of a task. Also remember the loops from the previous model. Finally, a balance between an individual and a collaborative activity must be found. The mission preparation process is a collaborative endeavor. We have seen the involvement of several actors in the model, each with their own timeline and constraints. From our theoretical contributions and those concerns, we can propose design opportunities. First, exploring safety on maps. Fostering systematic identification and exploration of operational parameters, RC2, RC4, with visual analysis on maps, RC6, can support operators exploring the design space and use spatial reasoning. We use this approach in a longitudinal study with a drone operator. Longitudinal study with a drone operator to explore how direct manipulation of operational parameters on maps could enhance the identification of risks in context and the formulation of adequate mitigation. Our results suggest that the visual analysis of safety buffers associated with drone trajectories helped adjust the trajectories to reduce the risks, which strengthens the validity of our proposition. Second, automating risk assessment. Our participants explained that multiple regulations, aviation procedures, safety methods, and values of operational parameters must be considered. Automation must support the user in understanding and mitigating the risks instead of simply trying to accelerate the process. Using the capacity of computers to apply rules, expert systems can accelerate risk assessments by providing information from a regulatory perspective and a safety perspective according to the concept of operation. Compared to other artificial intelligence techniques, the systems are more transparent and the reasoning can be traced back. There is also the support to collaboration. In other domains and consistent with our findings, collaboration can improve safety. The characterization of the different relationships between the interested parties and the possible identified improvements offer a new research perspective for computer-supported collaborative work. As conclusion, we now have a better understanding of drone mission preparation phase for risky missions despite their complexity. We propose actionable elements from field data. To improve both usability and safety, we can think about automating tasks, augmenting the reflection and creativity of operators, and supporting the collaboration between all the stakeholders. One of the main challenges is to integrate such a system within the workflow of the operator, rather than introducing an additional tool. Future work will focus on finishing an expert system for achieving computer-assisted drone operation risk assessment tool, and then its validation via field studies with drone operators.